Continuing with what we were doing in the previous lectures, the today's lecture deals with chromatographic techniques more in details, because we now have to understand each one of them more elaborately. Planar separation, both in plate chromatography as well as thin layer chromatography. Separations are halted before the mobile phase has travelled completely across the surface, which means that there is a limiting factor. Both in terms of the paper, there is a limiting size, and in case of TLC, there is a limiting size of the plate. Analyte or solute is characterized by the distance it has migrated relative to the solvent front. Solute retardation factor or RF is the distance travelled by the solute and the distance moved by the solvent. In this whole process, what is the Sobsen process? The Sobsen process is the process whereby solute species are transferred from the mobile phase to the stationary phase, and then by the mode of desorption being the reverse process. Adsorption, partition, ion exchange and exclusion are the four basic mechanisms, of which two or more may be involved simultaneously. So, do not get confused by the different nomenclatures, because the nomenclature depends either on the mechanism or on its mode of action. Qualitative and quantitative analysis. How does chromatographic technique help us in qualitative and quantitative analysis? We will try to learn this in the following few slides. Comparison of retention time for unknown solutes with corresponding data for standards obtained under identical condition. That means that we first run a standard. A standard means a compound which has a purity of 99% with respect to the unknown, and if the unknown is the same compound, then the retention time will tally under the conditions that they both have been run under the same machine system. If we alter any parameter, it would change the retention time. So, one has to remember that under identical condition, the standard and the unknown must be run in order to make a qualitative analysis. Spiking samples with known solute. In cases of trace analysis, where the peak may be very small, in that case an internal standard is added to the sample in order to increase the concentration of the compound per se, and that spiking is done in a quantitative manner, which means that suppose if the analyte is in trace quantity and we add a 5 ppm solution to it, 1 microliter of that, then it should show a 5 ppm plus a few digits after the decimal. Interfacing the chromatograph with spectrometer, that also helps us in understanding the quantitative analysis of any separation technique. Comparison of retention data alone are not always reliable, as many substances can have identical chromatographic behavior. Now, when we say that it is a method of calibration or it is a method of validation, it means that we are only making a comparative data between the standard and the sample, but it need not be that all samples which have the same retention time are the same molecules, because they could be different molecules coming at the same retention time. So, one has to remember that this is just a calibration method, an identification method, but not a foolproof method. Now, when we make qualitative analysis, retention data is of absolute importance, but it is not an absolute value. It is not a fixed value. Retention data can be used for some qualitative work. The retention data is characteristic of a substance compared to a standard. To be useful, some problems must be addressed. I will take a comparative analysis to show you that if the standard elutes at a retention time 10.2 minutes and the sample also shows a retention time while eluting under the same operational conditions at 10.2 minutes, which means that they may be identical because they are eluting at the same time. So, that is how we make a comparison between the retention data. Reproducibility of absolute retention data depends on several experimental conditions. Now, it is also true that under the same operational condition, the retention data or the retention time must be the same. A little bit change in the decimal can be from time to time allowed, but not otherwise. Now, coming to gas chromatography, we have just now understood the general phenomena of chromatographic techniques, but we must also now understand machine by machine how they work, what is the principle behind it, and what are the substances that can be purified by gas chromatography, and so on. Separation of volatile components of mixture solute must be thermally stable. Migration through column, which is thermostatically controlled. The solute elutes in the increasing order of their boiling points. Now, there are couple of things which need to be explained here. It is gas chromatography is meant for low boiling, which means volatile compounds. And when a mixture of such low boiling compounds are there, obviously there will be difference in their boiling points. Even if the difference is by just 5 degrees, the difference still exists and they will elute according to the rate of their boiling points. The solute must be thermally stable. That means that the analyte which is being injected in the gas chromatographic machine must not disintegrate, must not break down, must not decompose. Otherwise, what will happen? That the molecule which we will get after the separation will not be the same what we have injected. So, that much must be kept in mind, that the solute must be thermally stable. Migration through the column, which is thermostatically controlled. That means there is a temperature control throughout the column length, and through the column length the compound should not disintegrate or decompose. The solute then, when it elutes, will elute in the increasing order of the boiling point. That means the low boiling will come first and the higher boiling will come later. The detector generates an electrical signal that can be amplified and presented in a form of a graph or a chromatogram. So, now the data that is generated from a chromatographic machine is called chromatogram. Now, these terms must be very clear when we are talking in terms of chemistry, in terms of analysis. Retention relationship. Retention volume or time may be used for identification. For a homologous series, VR can be accurately determined, and thus we can say that if the peaks are coming one after the other, the peaks are actually belonging to its homologous series, that is they are different by a CH2 in their molecular structure. As what we know that the boiling point of butane, pentane, hexane is slightly increasing one by one. Similarly, the molecular size is also increasing by a factor of CH2, and such a series we call as homologous series. So, the same way there is a retention time relationship between its appearance on the retention time of the chromatogram. The bigger the molecule, the later it will appear on the chromatogram. Now, when we make an evaluation of any peak in the gas chromatograph, one thing that has to be kept in mind that the peak height is actually related to the amount of quantity that is present. Either we take the peak area or the peak height, but peak height is more easy to evaluate. In some cases you can assume that peak height is proportional to concentration, and that is what is made use of it when we are trying to do a quantitative analysis through gas chromatograph. The advantages are that it is very simple to handle, it is very simple to understand and to evaluate, and it is very rapid to make calculations, because you just have to measure with the help of the scale what is the peak height of the standard and what is the peak height of the sample. But there are disadvantages also. Height is more variable than area. Sometimes the peaks can be broad and they can be short. So, there is a deception, and there the results will not be accurate. So, that is why sometimes some people take into account the entire peak area, typically used for capillary column. But when we are using capillary column, peak height is the one which is more commonly used. Now, external standard method I have just explained a while ago, but I shall repeat again for you to understand, because it is important to understand what is a calibration method. As what I said, in a given chromatographic condition, in the gas chromatographic condition, one tries to set certain parameters. Under those parameters, the machine is operated, and the same parameter is applied to the pure compound, which is referred as standard, and under the same condition the sample is analyzed. Now, this kind of method is called external standard method. The standard is first run in the machine, and after a while the sample is run. The requirement for proper use are that a standard solution containing all eluents to be quantified. The standard must have all those components. The standard eluents should be of similar concentration as the unknown. Now, we have to understand that if we are expecting the unknown in the range of 5 ppm, we cannot take a standard of 100 ppm. The difference will be too large. So, we have to take in the range of 2 to 10 ppm in order to analyze our unknown, which is in the order of 5 ppm. So, that kind of range one must keep in mind, because an analyst should know that it should not go beyond the range of the standards. The standard and the sample matrix should be as similar as possible. Analysis condition must be identical, stable instrument, same sample size, and only then we can make a comparison. If the sample sizes are different, if the conditions are different, the retention time will be different. So, what will we compare with? We have to keep the operational conditions same, the sample size same, That means, if we are injecting 1 microliter in a capillary column for a standard, we will have to inject 1 microliter of the sample in the capillary column to be able to analyze and evaluate and compare. Detector response factor, it is a very important factor. Why? Because detector is the heart of a machine. That is what actually diagnoses whether the compound is present or absent, determines the actual response per unit concentration for a set of sample components. And that is why for a machine to be working in a proper condition, it is important to check the detector response, which means that concentration over area. Let us work with a few species, we call them 1, 2, 3. And now, if we have different detector responses, it will never show the same peak height, which means that the detector response is directly related to the reproducibility of the result. So, that is why it is important from time to time to calibrate the machine, to validate the machine in order to get the detector response in the proper manner. Internal standard method, overall the most reliable approach. The basis is that a known substance or a standard is added at a constant concentration to all standards and sample, and that is why it is called internal standard. Now, we will carry out only one run, no 2 runs are required, not that we are running the standard first and the sample first. In the sample itself, the standard but of a known quantity is added, and then it is evaluated one time. Now, that extra peak which the standard has made an enhancement is actually the amount which is present in the sample. Since the internal standard is always present at a constant amount, it can be used to account for variations such as injection volume during an analysis. Now, if I have to then explain to you what are the different methods of looking at the gas chromatographic machine, the first part which is very important is the gas flow, and obviously the gas cylinder must have a good regulator to control the gas flow. If the gas flow is very fast, all the components will be flushed out of the column and there will not be any separation process at all. If the gas flow is very slow, then the components will take hours to reach the detector. So, the gas flow must be very optimum, and that is what is very important, and this is the construction of the cylinder, and you see that compressed gas is filled here, that is called the carrier gas. There is a regulator which plays a very vital role. There is a valve which allows the gas to flow or stops the gas to flow, and there is a filter, because all these must be very purified gas in order to be able to do the analysis properly. Now, injection method. In this, there are several modes by which the injection into the gas column can be done. With packed columns of Gc, this is a pretty simple portion of the system. Two basic approaches are there. There is an injector port and there is a sampling loop and there is a valve. That means, first the injection is done and then the valve is closed. Once the gas starts flowing, then slowly the valve is released, but that is when we are using broader columns or packed columns. But in the case of capillary columns, the mode is only injector mode. Column, which is the heart of the separation process, because this is where the process actually takes place. A mixed analyte is converted into purified samples. Vast number of materials have been evaluated, it is usually best to refer to various catalogs as an up to date reference, because now there are tailor made columns for specific analysis. So, one can look at the catalog and choose the right kind of column for a typical analysis, and it can be classified by tubing diameter and packing type. That means, columns could be pack type, which are broader, and they could be capillary columns, which are almost of the hair size width. Covert retention index. This is also just like the retardation time or the retention time. Each chromatographic setup will vary to some degree. From time to time, from machine to machine, there is a factor which is called the covert retention index. Retention time for a known set of species can be hard to produce or reproduce from one lab to another, or even from one instrument to another. Retention indexing helps to standardize our results. So, that is how we try to look at these retention differences in retention data, but nevertheless the retention time on a given machine will not vary very widely. There are certain important influencing factors in the separation mode, and this slide particularly is very important. There are 6 major interrelated factors to be considered when one is analyzing or when is acting as an analyst. It is important to remember what is the column length, what is the column internal diameter, what is the film thickness in that internal diameter, and the carrier gas type, the carrier gas velocity, which is the speed of the flow of the gas, and the column temperature. If we do not take these things into account, one tends to make a lot of error while doing gas chromatography. That is why it is important to understand that there is a factor where we can do temperature programming. Sometimes if we have only 2 components in the analyte and we know that they have a difference, large difference in their boiling point, one need not have a ramp or a gradual increase in temperature. One can have an abrupt change in the temperature scale, but when one is trying to analyze components which have lower difference in their boiling point, one needs to do a programming of temperature. The column sits in an oven. If the temperature is held constant during the entire analysis, it is called isothermal. But if you vary the temperature during the analysis, you typically use a temperature program. So, this is up to the analyst to understand whether there is a need to have a ramp or a temperature programming, or whether one can carry out the analysis keeping a constant temperature, say at 180 degrees. But that is a little risky if you have both low boiling and high boiling components. One cannot jump into those very easily. Capillary columns. More emphasis has been made on capillary columns because in today's experimental conditions, more and more use of capillary columns are being noticed, because packed columns are meant for larger volume of analysis. So, the capillary column need a special attention. Major differences in the capillary column and the packed column is that they are smaller in their internal diameter ID. They are much longer in size. I said they are almost like 50 meters and they have been rolled up. No packing sometimes material is used, or sometimes very thin film of packing material is used. Smaller sample capacity. Because they are capillary columns, one cannot inject larger volume. Microliters of samples only can be injected and microliter samples only can be analyzed. This all adds up to allow components to remain on the column longer while still retaining good peak shape. Instrumental consideration. To account for capillary work, the injection and the detection systems must be modified. Obviously, we cannot have the same detector and the same injector for packed column and capillary column. So, there has to be certain modifications allowed for capillary column to be sized inside the machine, and therefore, the flow and sample amounts are much smaller in the case of capillary conditions. Peaks are much narrower, sharper. Detectors must be redesigned to reduce dead volumes and injectors modified to account for low column capacity and alternate injection methods. Now, here I would like to emphasize that many a times when even 1 microliter is injected, only 10% is allowed into the capillary column, while 90% is rejected, and this kind of injector mode is called split method of injection. That means the injection was 1 microliter, but in the 1 microliter also only 10% has gone into the column and 90% has been stopped from going into the column. That is why we call it split method. There are splitless method also where the entire volume goes through the column. So, even that precision is possible in capillary column. Injection methods. Capillary column have a much smaller sample capacity compared to packed column, almost like 1/100th or sometimes even 1,000th volume can be accommodated in a capillary column, whereas packed column can take 1000 times or even 100 times of the same amount. Methods are available to either reduce the total sample size by split injection or reduce the amount of solvent that enter a column by grob injection. That means the solvent is taken up, only the compound is allowed to enter. These are certain very specific techniques, but nevertheless I think it is important to mention these so that when you are reading from the books, you are able to comprehend what these terms mean. First, let us look at the injection system. Special procedures of GC. Non-volatile thermally labile materials can be pyrolyzed or chemically derivatized. There are now, the machine is now getting into more and more specific kind of analysis, and sometimes some materials which are non-volatile and which are also sometimes thermally labile, which means that they decompose at higher temperature, can be pyrolyzed or they can be turned into a derivative. So, we call it chemically derivatized. Headspace analysis. The vapors are sampled by a modified and automated injection system into the column. This is particularly useful in injection of alcohol in blood samples, flavors and perfumes. Thermal desorption. It is a preconditioning or pre-concentration step and can be used in conjunction with the headspace. So, now when there are gaseous samples, certain other modifications, because how to inject that sample into the gas chromatography for the separation, for the detection. So, these are headspace, thermal desorption, these are modifications to inject the gaseous sample into the gas chromatograph. Now, when we start understanding gas chromatography, HPLC comes automatically because it is meant for higher boiling compounds. But before proceeding for HPLC, I would now like to go back again to some more modifications of GC. Continuing with gas chromatographic techniques, I would now like to re-evaluate what we have talked so far. Gas chromatography is a method of separation which employs a gas mobile phase and either a solid or a liquid adsorbent on the solid or stationary phase. Gas chromatography is capable of separating very complex mixtures, and the selectivity can be adjusted to separate almost any given pair of solutes by judicious choice of the stationary phase. The major limitation of a gas chromatography is the requirement that the solute must have a reasonable vapor pressure at a temperature where it is still stable. So, that is a mandatory factor. We are just trying to re-evaluate and re-understand what we have studied so far. The first Gc detector was invented by James and Martin in 1952 and used for separation of some fatty acids. It consisted of a titration apparatus situated at the end of the column, and the eluent gas was bubbled through a suitable aqueous liquid to absorb the solutes. The solution contained an indicator, and each solute was eluted. The solution was manually titrated. The titration process was eventually automated, and an integral chromatogram was obtained by plotting the volume of the base solution added against the time. The integram consisted of a series of steps, one of each solute. This is a primitive arrangement. However, this is how gas chromatography started. So, you see, over a period of time, with the invention of new techniques, with more innovation into the machine, lot of things have got automated. Temperature changes during the passage of a solute through a theoretical plate in a gas chromatographic thermal changes resulting from solute interactions with the two phases are definitely second order effects, and consequently, as such, as Einstein predicted, their theoretical treatment is much complex. It is imagined that it is a plate theory, that it is going from one plate to another plate to another plate, but then it is much more complicated. The theoretical treatment of temperature perturbations that result from solute phase interaction, however, provides a good example of the use of the plate concept in a wider sense of chromatographic theory. Different chromatographs, let us just have a recap of what we have studied so far. Gas solid chromatography based on the adsorption or the exclusion principle on the basis of their size, and gas liquid chromatography is based on the partition mode. Now, these are different modes. Basic instrument contains carrier gas, analytical column, injector, detector, amplifier and recorder. Carrier gas selection, it is a very important and a crucial decision. In gas chromatography, the carrier gas acts as a mobile phase and the transports the sample components through the column to the detector. It is the main part which is allowing it to move. It is very necessary to select the best carrier gas as it affects both the column separation and the detector performance. Hydrogen and helium, having small ratio of viscosity and diffusion coefficients, are the best carrier gases which are most commonly used. Carrier gas must be chemically inert to avoid any reactions with analyte, column or detector. That means the choice of the carrier gas should be such that it should not chemically interact with any of the three, either the analyte or the column or the detector. Typically, it should be inert. Typical gases include hydrogen, nitrogen or helium and are delivered using standards. Pressure regulators with flow rate typically monitored using a soap bubble meter or more commonly a digital flow meter. Nowadays, the digital flow meter is the one which is used. Typical flow rates are 25 to 150 ml per minute for packed columns and 1 to 25 ml per minute for capillary columns. Choice of gas is often dependent on the type of detector that is to be used. Analytical column. The column is the heart of the gas chromatograph where fundamental separation process of Gc takes place. Column used could be of the packed type or the capillary type. Selection of suitable column. For non-polar columns, we use non-polar analyte uses non-polar column, and the boiling point differences should be much different. Ready-made column, tailor-made column, as I mentioned earlier, must be used from the catalogs that are already available, so that one can design the analysis and do it accordingly. The stationary phase. Stationary phase should show all the following properties: low volatility, that means the boiling point should not be 100 degrees greater than operating temperatures. Thermal stability, no pyrolysis should take place of the stationary phase. Chemical inertness, solvent characteristic that allow K prime value to fall into the useful ranges. Ideal stationary phases will show a range of different distribution constant for different analytes, but will not display very high or very low values of K, as these will lead to long separation times. So, what it means is that we have to make an optimum choice of everything in order to have an optimal analysis. Primary rule or the thumb rule is like dissolves like. Non-polar analytes will partition strongly into the non-polar stationary phase, while polar analytes partition in very well into the polar phases. Different detectors, I had mentioned earlier also, but this is just like a recap. So, we are trying to look at all the Gc components and important features one by one. Electron capture detector, flame ionization detector, thermal conductivity detector, mass detector, flame photometric detector, ultrasonic detector, nitrogen phosphorus detector, and many more. Injection mode could be direct injection into the packed column, split injection in the case of capillary column, splitless injection also in the case of capillary column, thermal desorption, cold trap injections, which are very specific for gaseous samples. Column used in Gc, the chromatographic column is used to contain the stationary phase. Columns may be made of glass, stainless steel, plastic, and many other materials. Some types of chromatography that utilize a column are gas chromatography. The Gc column can be packed, capillary, tubular, and thus the oven must be capable of taking all the different types of columns that can be seated in that oven. In general, the analysis carried out on packed column are likely to provide greater accuracy and better precision and repeatability. Packed Gc columns are usually made up of stainless steel or glass and are open tubular columns. But as what I mentioned, that capillary columns are the order of the day. Capillary columns coated with a large variety of stationary phases are now commercially available. Dedicated columns are available for specific analysis. Chiral columns are also available for enantiomeric separations. Column and column oven, because as I said, the column is seated in an oven. Gc ovens usually require an operating range of 5 degrees to 400 degrees, although majority of the Gc analysis are carried out between temperatures of 75 to 200 degrees. Temperature programming is an essential feature of all Gc column ovens and is necessary to handle a sufficiently wide molecular and polarity range of samples. Linear programming is the most common, although other functions of time are also available. The thermostatic medium of Gc oven is almost exclusive by forced air, as the heat capacity of the Gc mobile phase is relatively small. The temperature program can be controlled by a microprocessor incorporated in the programmer or can be controlled from a central computer that governs the operation of the whole instrument. Now, as I said, the temperature ramp can be given, or an isothermal conditions can also be carried out. Qualitative analysis by GC. Careful sampling and sample preparation is mandatory. Precise sample injection, auto-samplers better than manual injection. Appropriate choice of column and operating conditions are also very necessary. Detectors with reliable linear response have to be taken into account.